Alright, so the moment y'all been waiting for. Fam. So, I mean, first thing I'll say, so what we're talking about here is, well, I guess you can also probably tell from the description and the title, but we're going to be talking about functors, applicatives, and monads. And so there is some mathematician screaming somewhere that I am doing all of these together. And the reason they're screaming is that I am, almost disrespecting the, supposed complexity of these type classes. And I really don't think they are that complicated. I think they are explained in the most complicated way in the entire world. And I think that's more a reflection of I don't know, this is me going on a theoretical limb here. I think it's more a matter of how mathematicians see the world as opposed to how complicated these things actually are. They're definitely more complex to think about than other concepts, sure, but even, I don't know, complexity I feel like is relative and a matter of learning and how you view things. So I will say I spent a week, like literally a week, learning, like during COVID, when lockdowns were happening and you're at home. I was temporarily laid off from work, so I had quite a lot of time to dive into stuff. And I spent about a week on just applicative. And in hindsight, I have no idea why I did that. I know why I did that, but I don't think that was necessary. I do not think it should be necessary to learn Haskell, to spend a week on applicative. I think it is quite straightforward. And so I think all of this just really comes down to, like, how do you think about functors, applicative, and monad. And I think the first thing that needs to be said is that there is a very, very clear similarity between them. And so that's also kind of I think stated in the language itself about how the type classes work. And so all three of them, a functor, applicative, and monad, they're all type classes, and that's the core thing. And so I believe if we check out the info on monad, we see that it has to be an applicative first. So it can only be in a monad if it's also an applicative. It's a superclass. And for applicative, it has to be a functor. Yeah. And so this makes sense because, one second. So sorry. So yes, so all the type classes are related, and I think and the core reason is that I would say another way to say applicative and monad is like fancy functors. And now that's not necessarily fully true, because it's more so in the course of how we might be building our applications, we might get ourselves into, wrapper traps, let's say. Cases where, stuff is in wrappers. And there's really no reason, like, that we can't just throw away these wrappers and then go about our business. But that's actually kind of what we do anyways. But we do it in a way that keeps such a wrapper. And so you guys might remember how, the I/O lessons where I was talking about I/O, and we might do something like get line. So, so annoying. Why do I do? Oh. Okay, never mind. That was easier. GetLine. So getLine is an impure function, you could say, or impure IO action. And if we look at the type of getLine, you can see that's IO string. And so the point I was making in the other video was that this is, of course, not the same thing as a string. This would be very, what's the word I'm looking for? Well, what it would be is devoid of context. And that's the perfect way to say it. This is devoid of context. This is, yes, it's a string, and we can operate it on it like any other string. I mean, like quite literally, anything that we can do to a string, we can also do to an IO string. But, I mean, I think it's pretty agreeable to say that it's best to be clear how we got this string. That we have what's called referential transparency. So, you know, if we didn't have this IO string, and this is kind of what we have in Python. If we did inputs, I can probably get this. Excel P, Python 3.9 is it? Yes, Python. We do input. It's gonna ask me and do really the exact same thing. And if I say, what's the type of input? I'm not sure what it's going to say. I mean, it would probably... Oh. Well, my point exactly. Okay. Okay. I mean, I don't know. Brain just broke a bit. Let me recover. There is a purist side of me that just got a little frustrated. But I mean, what I thought would happen is that it would just show me directly class a string instead of asking the type of input, because I suppose that would happen with Haskell if there was an equivalent. I mean, and that's a different story, but so I won't get into that. All right, I have to do exit. And now let's get into Happy Land. And so yeah, so you know, this doesn't make any differentiation about this being a an IO string versus a string. And there's no referential transparency in how I'm getting that string. And so, you know, even just another point here is, like, what if I am taking input from a user, and, you know, of course, this is not the you know, this isn't how you would do web development. You wouldn't use input for web development. But you might even have let's say you have a gaming client which communicates with the server, and for some reason you've encoded it that, and this is also a bad idea, but you've coded it so that your server trusts your client completely. It just can do arbitrary stuff on the server. Then you could have a case where, like, you know, input not being clear about where that string came from could allow you to easily code yourself into cases where you just completely open up massive security holes. And, you know, so it's very important in the context of I/O, that we we know when we're dealing with an I/O context, because there's just a whole another added layer of complexity, and there's many things we can point to here, and the simplest one is that it could fail. It could be, we can't read from standard in for some reason. There's some sort of glitch with our Linux operating system. I don't know, or just simply security and referential transparency is, is really just in the simplest way, just a great way to make sure that we're writing good code, and that we actually truly understand what we're writing, and not writing kind of, I guess, code bloat, I suppose. Although I'm not so sure about the code bloat part. There's just so many reasons for why you need referential transparency. And so another interesting point that I mentioned is earlier in another video, I believe it was the I/O one, or I/O2, I should say, is that, it was I/O1 for sure. There used to be no possibility to do I/O in Haskell, or input and output in Haskell. You could only literally make heat on your computer. You could have this crazy function which computes the factorial up to the 5,000th or 500,000th or 5 millionth step, and but it could not show you what it just calculated. It could not even print put to a file what that was, because there was no way to show that, there's no way to do such an action with what was a wholly pure Haskell at the time. And so since then, with the invention of the monad and I/O, or the I/O monad, I should say, now you can do impure actions. And so Simon Peyton Jones, I actually watched a recent video on him talking about how the title of the video was that Haskell is useless, and I was like, what the heck? And I didn't get it at first, and he was kind of saying there's like this nirvana of a perfect language where you have a very controlled nature about how you can do side effects. Like, for example, we can't do side effects in the plus function, right? In this function where we add two numbers together, we are not allowed to do I/O, right? We can't print what we're doing inside of this function. And the reason for that is to keep plus as a pure function. And also, of course, we could not do get line inside of plus, because that would kind of just completely destroy the idea of a pure function and what plus is. And really, almost everything in programming that we want to build, assuming that we're building our code in very modular ways, very few, almost everything should be pure. The only thing that should not be pure are things that we cannot control, and that is stuff coming from the I/O monad. And so there's this kind of there's a word, endogenous, and I believe I'm not, well, you know what, I'm not gonna lie, I can't remember off the top of my head if it's exogenous or endogenous, but one of them means that an external variable comes into the model and affects the model. And so that's really, I guess, the scientific word for what is going on with academic word for what is going on with I/O and the actions that we do. So, functor. So let's start with functor because it is the first of the three classes. And so if we look at functor, well, let's just do this. Let's do info on functor. I spilled the beans there. So functor has two functions, and you know what? I'm just gonna, for the sake of simplicity, get rid of that function because it's really just defined in terms of fmap, anyways. I mean, or I don't know if it actually is, but it's extremely similar to fmap, and fmap is the core function that we care about. So I'm also just gonna copy this over, and we have this here. So what is this? And I guess if I had to copy it over here and take it away from its class, I have to say that it's a constraint on f. Okay, so where's f? Well, it's not in this function here. I can see that fmap is a higher order function, where that function that it takes in is from A to B. And then, oh, I have this FA. Oh, this looks new to me. Huh, what could this mean? And then I also have this FB. Huh, what could this mean? Well, I mean, let's assume we know nothing. And I mean, I'm just looking, and well, we don't know nothing. We know how to read type signatures. And so I can see okay, first off, we have a higher order function. So this higher order function must be using the input, or the given function as an argument. That given function somehow in its other parameters. So the only other real parameter here is this FA. I don't know what FA means here. Maybe you do. Maybe you've guessed it. But let's say I don't. So, but I can see that A is the same type variable as this one. And so in this function, A is an input that returns a B. Well, it's curious because my return type is this FB, and I still don't know what this F is, but I know that it gives me a B. So, I mean, you know, if we were to take away this, for example, it'd be really straightforward. I don't even know if we'd really need that. I mean, well, I guess we could write a function like this where we have, you know, my funky funk, and it is going to take an A to B, and then it's also going to take an A, and then it's going to return that B. What even does? I don't know. What can I apply this to? F, A, and then A, so I guess I would just apply, well, this is what I would do. I would just say func A. And my funky funk, what could I even call this on? I could say, oh, and I'm going to need to import this into main, import fum. So I don't got friends, I got family. The first part's true. But, so, jeez, dark. But, so, my funky funk. I guess, okay, we could easily apply this to ID and 1. Oh. And that will work. Maybe something more exciting would be 1 plus something. And that gives us 2. Okay. 1 plus, I guess that's sort of useful if we want to have a function which adds 1 to stuff. Cool. But anyways, let's get back to fmap. Actually, I guess I don't need to delete that so much as just comment that out. So our real type signature here, and I'm going to spend the most time probably on functor, just because, again, if you get functor, you really, trust me, you get applicative, you get monad. Especially applicative is really not a far cry from fmap or functor. And so what this is saying now, in going away from the type signature, what this is saying and how I will explain this is that if f is just some context, this simply means some context. So, for example, this could be IO. And if we check if this works, if we look at IO, we see it's a functor. So this does, in fact, hold true. We have not done anything weird here, or illegal, I suppose. And what this is saying is we have a function from A to B. We have an A, which is wrapped in this IO wrapper, or, and this IO wrapper just meaning that it's in some IO context, right? Or we've gotten it from some IO context. This could be anything from we just simply placed it in this IO context to it literally did come from an IO context. We read a file, right? We have a type of read file, which is going to return us an IO string. So a string wrapped in an IO wrapper, and from the IO context. And we also have getLine, which we saw, also gets us a string, just doesn't take any arguments to get us that string. There's only one way to read from standard in, of course, and that's to read from standard in. What else could we do? I guess if we did HTTP LBS, if it's in scope. So doing a web request. We see that we have an IO response. So different from a string, but it's still a type. And it will always be that type, of course. It's still that some type wrapped in IO from the IO context. And so, again, really working backwards here, we need to model somehow into our code that it came from IO, or that it came from some context, in this case IO. And so the best way to do that is with a wrapper. We're just wrapping it in that context. And so that sets the stage for why we need something like fmap, because now especially with IO, this is we cannot unwrap IO. It is impossible, just with how the language is defined, and what not even with really how the language is defined, but the IO wrapper is not exported unless you there are ways around that, but you don't, you are able to do unsafe. It's not like the language stops you from being able to ever do unsafe operations, but they make it challenging. And it's like, you can do this if you know what you're doing. But yeah, anyways, so let's assume, assuming, you're watching my channel, you're probably just starting out with Haskell, and so I think it's a fair assumption that none of us are trying to do a research paper in Haskell at this moment. Maybe in the future, hopefully. But yeah, that's where we're at. So anyways, back to reality. To goes gravity. And so fmap allows us to wrap without pain. And so let's say so IO we can't really use as my next example because I can't really deal with the wrapper here. But what's a different functor here? Maybe it might be a good idea. Aha. So if we were to write, well, the fmap for maybe, or let's forget about that for now. What I mean by, just to be clear about what I mean by the wrapper, is just would be a wrapper in this case. And so actually, let's even do a simpler example, because there's a bit more complexity with maybe that we need to understand. That really does come into our understanding of functor. So we also have this data type identity, which is very dumb. It does nothing. And so, in actual use, it's really just used to diminish the power of stuff, which I will not mention for now. And so it's simpler than maybe, in the sense that we only have one case. And so I'm just going to comment that out for now. And so our wrapper in this case is very clear. It's identity. So let's say we wanted to do fmap for identity, and we had A to B, and we're also going to take an identity A. So we're setting it up so that it has the same type signature really as fmap, and we're going to say copy paste func, and what we're going to do here, so if this is identity, how we're going to write this function, well, what I would do is I would not write that. I would say X, just for fun. I would say, well, here's exactly what I'd say. So, and how I get here. I know that I have to return an identity B. Like, I have to keep it wrapped in this context. And the reason I could, there's no reason with identity that I have to keep it wrapped in this context. But the point of fmap is to keep it wrapped in its context, to not destroy the context, but also do an operation on the variable bound to that context. And so, again, I could literally just make it like this, and then if it's, let's say I'm just returning B here, well, then this is really simple. I just say func X. But if I want to return an identity B, so I keep it wrapped in this identity context, I just simply say identity func X. So if you remember this operator, this just says everything to my right I will do first. I will evaluate first, and then I will pass it as an argument to the left of me, the function right left of me, immediately left of me. Yeah, and so it's kind of like brackets in the way that you could do that, but I am lazy and I don't like writing two brackets. It's a lot. And so yeah, we have built the fmap for identity, and we could look at the actual instance. Again, functor is a type class, so we will look at that in a second. But yeah, and so all I'm doing here, and this is always really true. Like in terms of the actual implementation, this is actually what we're doing. There's no such thing as like so how fmap is usually explained is that we're lifting this a to b over IO or over the f or functor, and like, you know, really what that means is this statement here, that we're unwrapping it, we're applying the func to the x in plain, you know, bare nakedness, and then rewrapping it with identity. And so that's what's really going on when we say that we're lifting over a functor. You know, maybe it's a nice visual, and it kind of did help me think about the core of what we're doing, but and I encourage you to think in that way, but just know that in terms of what we're actually doing, we're really just unwrapping, applying a function, and then rewrapping. Yeah. You know, also too, I mean, like a compiler doesn't have a concept of jumping. It just has a concept of unwrapping, applying functions, and yeah, even wrapping really is a function, where identity, we look at the type of identity, it just is a function itself. So we're just unwrapping or pattern matching and then applying functions to build our return type. Is an even more correct way of saying it. Yeah, and so now what about and so this was really simple because in terms of our pattern matches, this is all that we would see for identity. There is only one pattern of identity. There is not some other pattern that we can match. What about maybe, though? And this is where it starts to get a little bit conceptually challenging. And functor is more about a pattern that is very common in Haskell, as opposed to, you know, like, I think it's one of those type classes where the type class itself is a little disconnected from what the actual data type itself is. And so we can make maybe a functor, and we'll see how that is. It just might be a little confusing. And so the key point that I think will help your learning is, like, don't expect the functor instance of maybe to behave the same as identity. The functor instance is really to, I would say it almost helps to model the use of that type in practice. Like, for example, let's say the easiest example with maybe is we have a form, a web form, and we want to if there are no errors at all, then we will send a web request to the backend with the data that we have attained. And so a good way to do this, to model this, would be with maybe, because we'd have input 1, input 2, input 3, input, you know, all the way up to n. So these could all fail. And so this will either be, let's say this is a just a valid input of, their name, and we'll say their name is Galen. And then I'm really new to computers, so my email that I give is just Galen. And I'm like, I think that's right for some reason. So I give Galen, and then when I try to validate it, this becomes nothing because I cannot validate it as a real real email address. And then I go along, I get just something else, and then everything else is successful. But the form itself, the form as a whole will not be successful because I did have a failure. And so I should not send the web request. And so I can model that behavior that I'm trying to talk about here and trying to get through maybe. And so what will happen in the case of the maybe monad is it will say, okay, just Galen, and then it will kind of continue to put together this form, and Galen will fail. And then it will short circuit out of the maybe monad, and then never do anything. So how is maybe actually defined as a functor? So this is the functor instance for maybe. And so I'm going to come back to this here, okay? Just so we all are aware. And fmap, some f in the case of just x is one case, and I'm just going to put that for now. Fmap f in the case of nothing. What do we do here? So in the case that it's just x, and we have some value wrapped in maybe. I'm saying that, in the more general sense, like, we don't necessarily know if a value is just. I mean, it's great if we know that it's just, and I guess there are ways in which we can figure this out, but not in clean code ways. We can't know ahead of time if some variable is going to be just. If we have, multiple different inputs. I'm assuming that we're, actually trying to create side effects with our program, and we're taking input from the user and then conditionally doing some output. So, based on a number of logical checks on that input, which lead to what our end output is. So, this would be our answer in the case of just, because we're just able to simply apply the f to the x. And that's just like identity, once again. Here in the case of nothing, so this is confusing. We don't know what exactly the answer is here, but we can just go back to the fmap type. So fmap takes, I'm just going to copy it over. Lazy. So fmap must return some fb. So what would that be in the case of maybe? This would be a maybe B. What is a valid case of maybe? Well, we see that we have just A and nothing are two valid cases. In the case that we have nothing as our input, should we return just A as our output? I mean, no, because first off, let's try to build this. What do we apply F to? We don't have anything to apply it to. So this doesn't make sense. The only other option in this case is nothing. Does this make sense? We're basically conditionally applying F based on if we had a successful result or not. So, so a good example of this is if we did, I'm going to set my prompt to if we did fmap +1 to just 1, we'd end up with just 2. And, so for whatever reason, earlier on we had some successful case happen, and now we're just trying to work with that case. So, we could have this F here could be like, what should happen with the successful case, if you want to think about it that way. And now if we have nothing, we just give back nothing. And this makes sense. This kind of validates my point here, or the instance I've written. And this makes sense. Like, if we had some unsuccessful case, and we could in theory have found what that unsuccessful case is. Like, let's say we only wanted to return if it's wrapped in just, it should be a positive integer. If we and we need it to be a positive integer for some reason in our application, then but somehow we get a -1. So in the case that it's -1, we've returned it to be nothing. And so, we've made a clear distinction, a clear statement to the rest of our program, or the following evaluation of our program, that this was an unsuccessful case. And so while we could add +1 to -1, why would we want to do that? I mean, that's an unsuccessful case, and anything that we could do with it is just invalid in terms of our program and what we want. It makes sense to just simply throw out that F, right? I could literally say here that I do not care what F is in the case that nothing is there. And, So, now, so before we move on, I mentioned at the beginning that we are talking about classes which have to do with structure. So, So, typically, so with any other type class that we've kind of gone about, let's say EQ I'm just going to keep this here, but let's say we were talking about instance EQ, and we were talking about EQ for car, and we want to see if two characters are the same, and we implement the EQ in the most efficient way possible, blah, 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 blah. Cool. Anyways, what's different about car and maybe? Well, if we were to do EQ of maybe, we would say, do you see what's different yet? We would say EQ of maybe A. And that's because how on earth would we do equality with two type constructors, or a type constructor? Or, I guess equality between, a type constructor and itself. I mean, either way, it just doesn't make sense. A type constructor is something that builds types. So that's where the kind of the abstract nature of, of functor, applicative, and monad come in, is that we are actually making a statement about the about the type constructor, and so this FA, this is always something. So it just getting away from everything here, because that doesn't really tell us enough or anything. Well, it does tell us something, but not nicely. And we've seen this before with FB and FA. What do we know about the kind of F if it's in this, FB? Well, okay, let's again put it back to maybe. And what do we know about maybe before it has its singular type argument applied? And so if we look at the kind of maybe, we see that it's awaiting a singular type to become fully applied. What about the kind of IO? They're the same. Okay, well, what about the kind of identity? Peculiar. This is interesting. I do not understand, but I do understand. These are all awaiting a singular type to become fully applied. And so you can see this. This is actually not how I'm used to seeing it. I'm used to seeing it, for what it's worth, like this. I don't know if I'm just misremembering, and speaking out of my certain area, but yeah. Anyways, the key constraint to the class of functor is that F, whatever this, what's the word? What was I using before? Concept. No, that wasn't it. Whatever this. Frig, my brain is blanking. I had such a nice word for it, and it was so useful. But whatever this F is, whatever this this is breaking my brain. But I don't really before I was saying you could ask the info on any construct. That's what it is. I knew it was there. Construct. So this construct of F, which I guess we know to be a type constructor. So what good was that word? Anyways, we know that this type constructor has to be of kind star to star, or take a singular type in order for it to be a valid functor. If I was to say, let me just... instance functor int, where this should give me an issue. Yes, exactly. So it's impossible to write an instance of functor for int, and the just the kind of like plain English reason for that is int cannot contain anything. Int cannot wrap. It cannot contain anything. So yeah, it makes no sense as a functor. And so yeah, it's just not of that set of functor, I suppose, is the mathematical way of saying it. But what sense do I care about that? Yeah, and that's the key important thing to, I guess, know about the restrictions around functor. But the core important piece to understand functor is just simply that it is a wrapper. And, there's various reasons why we need these wrappers, and especially as you do some practice in Haskell, you'll see, why these cases where you have a wrapped thing naturally come up. But and even too, like another reason why they naturally come up, I'm thinking about reflex, is that it really allows the library creator a lot more power, and that they can allow you to do very simple things, but can create sort of this like land of almost like I want to call it like a land in their library, where it's just like things behave in a certain way, which makes sense for that domain. And that's even getting a little complicated, a little abstract, but yeah. There's the point is there's reasons. There's good reason for why certain values will be wrapped. And so since certain values are wrapped, this is a problem and we need a solution, so we have functor. And lastly, just tying off the knot, fmap is our minimal function that we need to create for this class, and then we have all of our other functor functions like this guy. So the other case I'll say is, just for the sake of completeness, is either, and so and this goes back to the star thinking, is that what so we're gonna do some Dora the Explorer here. Where I'm going to ask you a question, and you are going to respond, but not in any chance of my earshot, unless you are my neighbor, in which case, hello. So which one do you think is correct, and why? I encourage you to pause the video right here and just kind of think it through for yourself. But which one is correct? Now, pause. Okay, the reason that this one is correct is that the type of either, kind of either, is star to star to star. So this doesn't. These three stars are not the same as these two stars. But if we had either string, for instance, then we do have something that is a valid functor. And it's not because of the string. I can't just say a here because it'll get angry. But either with one applied variable or one applied type variable is a valid functor. And so how does that actually look? And I think it's important to write the instance of functor here for either, because what we'll see is it's pretty much just maybe. It's like and why does that make sense? It goes back to what I was saying about kind of distinguish the the generality of like a functor type class from how functor helps to model a given type. Like a functor instance is far more about what that actual type is than what functor is. Like functor is very, 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 very overloaded as a term, and so we've seen that maybe and either are very, very similar. My video on exception handling, or pure exception handling, will be out by now, but like we can see that they are very, very similar in how they are used, and where they're used. Yes. So we look at this, we have fmap f, and again, this is just how we write any instance, I suppose, which you can see from the type classes video. And so we have write x, we are going to have not 8, but write f x. Just like with just, we had just fx and we have write fx. They're largely exactly equivalent. Like there's really, what's the difference? Tell me the difference between a write and a just. It was just two different ways to model what ended up being the same result. So now if we have left e, we're just going to do left e. We're just going to give back left e. And so I don't believe it would even be valid if we tried to apply f here, because it'll give us a very particular error, and the compiler is really smart. Right. I'm just going to say data either... you know what, this case it's going to be easier to just say no implicit prelude. This is just for tutorial purposes. Why is that happening? Oh my gosh. Now I'm just going to say data either AB equals left A or right B. Fair. Import prelude functor. Fair. That's also fair, I suppose. Yeah, and so this is the error that it is going to give us. It's not very clear on why it's failing, but I'm sure there's a way I could show with the type of fmap. Well, it's kind of more like this. Like it doesn't. So nothing about this syntax or signature. Nothing about this signature and the information it has about f tells us anything about A here. I'm going to say E. Yeah, I'm going to say E just because E typically isn't, either error or the thing we're looking for. And so F, it knows about F, and it knows that F must be an A to B. But it has this instance declaration has no information about what the type of E is. Or, well, not that it has no information about it, but it cannot. I guess I think the most accurate thing to say here is that it cannot guarantee that E is going to be the same type as this X, right? E and X are not necessarily the same types, and that's because of just simply how either is defined. There's nothing, right? If this was the case, then maybe that would work. No pun intended. But it knows that they can be different types, and so there's no guarantee that they are the same type, and so the compiler cannot handle that. There might even be such a thing as a language extension, which allows you to get around that trick, or get around that with a trick. But I don't see why you'd want to do that anyways. And the compiler is very smart. It can tell when you're trying to do something that is not type safe. So yeah. Anyways, so how much time did we spend on? Wow. Oof. Okay. It's a lot of time. Huh. Interesting. That was a lot of time on Functor. But it was also kind of... you know what? Okay, so I'm gonna do this as a 3-part series. Is what I'm gonna do. So I'm gonna end off this video here, and this is part 1 of 3 parts, and yeah, and then the next 2 parts will, I guess I'll break it up into applicative and then monad, which is probably better anyways. I think this is kind of the best of both worlds because I wanted to combine the 3 to make certain points, but I think it is also best to break them up in terms of the actual concepts, although the concepts are very similar. So, with that said, fam, good night, or, well, not good night. I mean, I'm going to continue filming, but, yeah, so, if you're not taking along for the next video, or not taking along for the next video at this exact moment, bon voyage, and have a good morning, afternoon, night, or whatever you like to code. Happy coding, blah, blah, blah. Yeah.